Is,
Hello, everybody. One of you could answer so that I know that I'm being heard.
You're good. Hello.
Thank you. Yep. So, few announcements before we begin the lecture. Let's see. So we have homework 2 due on Tuesday. I have posted the homework 2 solutions. Like earlier, the solutions are primarily oriented so that anyway, the solutions are mostly available on the internet, and as well make a roughly similar kind of solutions made available. So I changed the problems to a certain extent so that you still have to do a little work, and it is done in the notations of the class, so that makes it a little easier to grasp. And remember that if you're using the solutions, I encourage you to use the solutions, nothing wrong, but be responsible that remember that you have used it, and make sure that you don't assume that, oh, I looked at the solution, I understand everything what's going on, so I'm fine, because in the exam there will be a time constraint, and that might be a wrong assessment for yourself. So just be aware of that. That's all I would say. So with that, I should also point or before that, I should say midterm, right? So midterm 1 is 1 week from Tuesday. And this will be during class period. Notice that as part of this online course, it is necessary that you learn how to submit files. Almost everyone except a handful of you are able to submit files easily, but those who are not able to submit files, you have to learn to do that. Ask your friends or ask me or ask the technology service. However, it's relatively simple, just a small discussion with one of your friends might solve the problem, or feel free to send me any email or however you find it convenient. That's very necessary. I'll be a little strict about it because it's a way assessment works. If it is not available on D2L, it's not going to be graded. Sending the file to me is not a replacement of submitting it on D2L. So make sure you get all this cleared up in the first homework. So I think again 90 to 95% of you are already smooth, but those of you are still working on it, learn it. So submission of files has to be as a single submission, multiple pages. Learn to do multiple pages as a single file. If you're struggling with it still. Okay, so that's one thing. What else? Yeah, chapter. So 3 chapters I've scanned. Chapters of 9th edition has been posted on D2L. It's behind password, and I'm told by the library that it is okay to post chapter-wise on D2L. So that might be convenient for those who haven't got a textbook yet. So submission, homework, what else? Yeah, that's all, I suppose. Any other questions you can think of right away that I should be addressing? Okay, now let's proceed. Let's do some examples concerning kinematic equations that we introduced last time. So we are mostly discussing motion in one dimension. So these are also called kinematic equations in one dimension. One dimension means that the motion is happening mostly on a straight line, so it doesn't matter what else is happening. So one dimension has to do with motion happening in.
I have a question. Would this be counted as chapter 3 notes or just still chapter 2?
This is chapter 2, I think. First chapter is on mathematical, a preliminary mathematical equation, including vector algebra, and this is chapter 2.
Okay, thank you.
Yeah, we will try to go chapter wise, like one chapter in a week. So each homework will be per chapter. So one homework in a chapter. If I'm doing anything different, more probably I'll label the homeworks differently, something like that. So mostly this is, this is chapter 1, that's answer. Okay. So, sorry, chapter 2, did I say it wrong? Still chapter 2, last lecture also we talked about chapter 2, and still we are in chapter 2. So we're talking about motion in a straight line. Straight line could be either horizontal or vertical, or for that matter, in any direction. Pick out that direction, make a straight line out of it, and imagine it as a straight horizontal or vertical, doesn't matter. Usually throwing a ball up is a good way to picture what's going on. So vertical is good, but whenever you're thinking of driving a car or something, then horizontal is also a good way to look at it. The variables that comes in picture are time, and instead of talking in terms of time itself, we talk about change in time. It is not the time as it evolves, that is the final time and an initial time, but the final time, if you think of it as a variable, then it is continuous. In that sense, it's a continuous variable, and this is delta t. Displacement is a change in position. X is the position, and we talk about initial velocity, final velocity, and acceleration. And we introduced these ideas last time. We introduced 5 equations. So let me rewrite them here. Delta x over delta t is v initial plus v final over 2. This is the definition of velocity if you want. Acceleration is v final minus v initial over delta t, which can be rewritten in this form. So if I imagine this to be on the left-hand side divided by acceleration, then it's, divided by delta time, then it's a definition of acceleration, but it's often rewritten in this form. There are 2 more equations for distance, how distance evolves in time. So this is one equation that tells you how distance changes with time. Notice that it depends on the square of time. So as time increases, the distance increases significantly faster. So 1 square, 2 square is 4, 3 square is 9, 4 square is 16. So very quickly the number increases instead of linear. Linear means 1, 2, 3, 4. Quadratic means 1, 4, 9, 16, 25, 36, and so on. So motion, when it is happening on uniform acceleration, goes quadratically. Delta x is Vf, delta t, there's one more equation with a negative sign. Notice I changes to f. This is delta t squared. And finally, we have v final square is equal to v initial square plus 2 times a times delta x. There is something immediately we should recognize, that we call something as missing variable, and as we do examples, this will get clearer what missing variable means. In each one of these equations, one of these 5 variables is missing. This has a missing in it, this has delta x missing in it, this has v final, this is v initial missing in it, and this is delta t. So, so practically speaking, this is what we are dealing with here is motion with uniform acceleration. Acceleration doesn't change. Uniform means constant. So acceleration doesn't change with respect to what? Change with respect to time. That's not always true when you're driving your car, for example. That's not true that acceleration does not change. Acceleration changes. So this is a simplified version of what happens in real life. So this is not the complete story, but it is very easy to extend this, and it captures a lot of physics already in there. And why do we restrict ourselves to this? Because we're trying not to use calculus. We're trying to avoid calculus as much as possible. So that's a limitation of this whole scenario. But we will consider situations only where this happens, and and you'll see that it is pretty rich in that. Another similar scenario is motion with a uniform velocity. So these are the two different, two kinds of motion we will deal with, two relatively simpler, simple scenarios. When it is uniform velocity, out of these 5 variables, uniform velocity means that velocity does not change. So initial and final is the same, and acceleration is immediately equal to 0. Acceleration is equal to 0, and initial velocity is equal to V final. That's the requirement of initial velocity, uniform velocity. It could be static. That's one simple scenario where it is just staying at rest, all 3. But if it is moving, then you have only 3 variables now: delta x, delta t. Let me start with time. Delta t, delta x, and v. It doesn't matter whether it is initial or final, so we'll just call it v. So that's significantly simpler. Only 3 variables instead of 5 variables in uniform velocity. And there's only one equation. And the equation is delta x is equal, or delta x over delta t is equal to v. That's it. It's significantly simpler. And you will notice that each one of this equation, if you put in acceleration equal to 0, you will get that equation. You will either get this relation, or you will get a equal to 0, or you will get this equation. For example, here delta x over delta t, because initial and final is the same, so you get exactly v is equal to delta x over delta t. Here acceleration equal to 0 means initial is final. Acceleration equal to 0 gives back that equation, and here if you put acceleration equal to 0, the initial is equal to v final. So that's the 2 kinds of motion that we will be dealing with. A special class of problems we will be discussing is what is called free fall. So let me change the camera. So a special class of problems will deal with what is called free fall, and in the same context, or for that matter, in most of what we did here, I should say that air resistance should be neglected. Unless specifically said, we're going to neglect air resistance. So what that means is, so let's ask the following question. If I were to drop a feather and a stone, like think of something heavy and something light, and you could ask which one will reach the floor first. So there is a small demonstration you can do. So think of, so this is a heavy. Well, maybe I should zoom out. Let's see if I can do this. Let's see. Zoom out. No. Yeah, that's it. Reasonable. Do you guys see the floor and a file and a sheet of paper? Correct?
Yes, you're good.
Yep.
Yes. Now I'm going to drop these 2 so that it falls on the floor. And I would ask you guys to guess before that which one will reach the floor first.
Heavier.
The heavier, right? So that's correct, right? So the heavier one reached first. But now I'm going to, so what happens is that that's because of air. So what I'm going to try to argue is that this is because of the air that actually this one lagged behind. Now we want to imagine a scenario where air is not really affecting this sheet of paper much differently than the heavier file. So for that purpose, what I'm going to do is I'm going to place this sheet of paper right on top of this file, and then again drop it. Okay. Now What's the difference in the two scenarios is that this sheet of paper is no more experiencing the air resistance from the air. And now you will notice that they will pretty much very closely reach the ground at the same time. Is that clear? Did that help?
Yep.
Yeah, so the point I'm making here is that if you could imagine there is no air, that means you suck out all the air from a room, let's say, and you were to drop a heavy object and a light object, they will fall at the same rate. They will exactly fall at the same rate. So there's a nice video for this purpose, which I have posted on the course webpage, or you can search on Google. So I think it is BBC video. So search for BBC and feather and bowling ball. I think these three, it's a very popular, it's a 5-minute video, 4-minute video, pretty nice. It describes this very well. What they do is, so there is such a room, you can build pretty big room where you can really suck out all the air and create as closely as possible as a perfect vacuum you can have. And then they drop a bowling ball and a feather. So here's an extra credit for that, right? Since I want to encourage this thought. So think about or comment on why this happens, right? What would happen if one object fell, or the heavier object fell faster than the smaller object? And it is important that we address such questions because long back, like about if you go 2000 years back in the time of Aristotle and Socrates and others, they all assumed that actually heavier ball falls faster. So the question is, if the heavier ball were to fall faster than a lighter ball, how differently, what will change around us? Yeah, put it like that. So just think about it and explore the possibilities. Look up the internet, read about it, and so on. Okay, so that's one of the extra.
I'm sorry, can you repeat that, please?
So
Yeah.
if air resistance was not there, two bodies, whether it is heavier or lighter, they all fall at the same rate. That's what is true. That is the correct statement. But now let us assume that heavier objects fall faster than lighter objects. What would happen? How would things change? The question, maybe I can state this better, okay? So this is, first let me say it as a fact, which is a true statement, is that all objects fall at the same rate if there were no air. So now extend this question. What if heavier objects fell at a faster rate? Remember that extra credit problems are completely exploratory, right? Exploration. It's based on exploration. So it's just for participation. You can pretty much write anything related to the subject, and that is sufficient. Often it is, as you guys asked me, it is not very obvious what the question is meaning. So you should state the question also. So state your question and answer it. Anything related to the context that's good enough. So that's the idea. Okay. Okay. So then the question comes, okay, if everything falls at the same rate, then the question is at what rate? At what rate? By rate we mean acceleration, right? With what acceleration do they fall? That means if I were to drop this chalk right at that point, velocity is 0. I want to drop it so it increases its velocity. As it increases, if the velocity is increasing, that means there is acceleration. Right? At what rate is it increasing? And that's decided by the gravitational force exerted by Earth. And we will do a much more detailed study of gravitational force by the end of the semester. Somewhere in between, we'll talk a little bit about gravity, and that by the end of the semester, we'll have a proper detailed discussion. But for now, this is a consequence of gravity, and this will be called G. Acceleration is going to be, it's going downward. So if I choose my upward to be positive, notice this depends on which direction I choose my positive direction to be. If the upward direction is positive, then acceleration with which everything falls is 9.8 meters per second squared. And it turns out to be the same for every object. Every object will increase its velocity as it falls with this same rate if air resistance was to be neglected. And air resistance depends more on the area of, like for example, when you're skydiving, you're experiencing a lot of air resistance. So for them, the acceleration due to gravity is different. Not that acceleration due to gravity is different, it is because there is a force. So the acceleration is different, but the acceleration due to gravity itself remains the same. So this is going to be one number we need to be aware of. So everything falls at the same rate. So we will, since this negative choice depends on what direction you choose for reference, often we will use the letter G to represent the positive quantity alone. That's 9.8 meters per second squared. In fact, it's such a standard number that everything is measured in terms of G. For example, just to give you an idea of where you use this, often if you're in a roller coaster, you would see something written outside that you can experience 5 times G in this roller coaster. 5 times G, so roller coaster typically. So roller coaster. The roller coaster is whatever we see in these amusement parks, right? So when you go up and down, they give you a feel for G, but in those circumstances, they generate a higher G. Basically, when you fall, you're falling under gravity. If you were forced to fall faster than gravity, that's an experience of a higher acceleration due to gravity. And roller coasters can give you an effect of about 5 to 6 G, right? So let's say 5G. 5G means approximately 5 into 9.8. 5 into 9.8. So if I say this is 10, that's approximately 50 meters per second squared. We feel about 10 meters per second squared, 9.8 meters per second squared. So roller coasters have this effect of giving 50 meters per second squared. Now, it turns out that our body has evolved to be afraid whenever we are falling, right? Falling has a sense. So we have a sense for this 9.8 meters per second squared. So if we realize that, oh, I'm falling, I'm supposed to be afraid in the sense, oh, something dangerous is happening. I don't have the floor underneath me anymore. So we have evolved to sense that. And 4G and 5G is approximately where that fear becomes really significant. And that's why you have that amusement parks use this property of human beings, that they get afraid. And that's why you typically 5G to 6G is what they try to cross. If you cross 4G, that means it is typically a significantly, what is it, effective roller coaster. So they will really ignite the fear in you. Fear, or sometimes fear also leads to amusement, right? In the sense of adrenaline comes in and you feel happy about it. So that's how a roller coaster works. Where do you experience a higher acceleration? A fighter jet, right? A fighter jet can experience all the way to 50 Gs. And if you keep increasing, for example, about 100 G is dangerous in the sense our capillaries, our blood vessels cannot tolerate it anymore, so they can rupture. So that's really dangerous. And 200 G is where it really ruptures out, and this is death. And this is what happens in a car crash. So if you're having a car crash, what is practically happening is you're going with some velocity. So let's say 70 miles per hour, and you're come to stop within a very small time. So remember, acceleration is equal to change in velocity over change in time. So if my final velocity is 70 miles, or initial velocity is 70 miles per hour, and final velocity is 0, that's change in velocity. But if it happens in a very small time, smaller the time, larger is the acceleration. And larger the acceleration, more is this, and there is a very good chance that it can lead to a rupture in your capillaries, and that's how that leads to a real death in scenarios when it happens too quickly. So that's a simple feel for what acceleration is about. But what we want to take home primarily is that everything falls downward with 9.8 meters per second square. That's acceleration due to gravity. So we will call this acceleration due to gravity. And if we want to think of its directional sense, then acceleration itself is minus of g. If my choice is positive upwards, it is plus 9.8 if my choice is positive in the downward direction. And in general, any object falling when you throw a stone and other things under, when air resistance is neglected, is what is called a free fall. And unless specifically said in a problem, we are assuming that it is a free fall. Okay. That's what we are discussing. Let's do a specific problem. So, example. Let's say you're driving, right? And so that's your car, right? And you're driving with some initial velocity, let's say. So that's your initial velocity. Right? And let's say you're moving at the speed of 50 miles, let's say, yeah, 50 miles per hour. Now, this, I specifically said 50 miles per hour because that's the units we are familiar with, but I also said that meters per second is what we should be using, especially because 9.8 meters per second square is given in meters and second square, so we have to be consistent with units. So either convert miles per hour into meters per second square, or use convert 9.8 meters per second square into miles per hour square. But we will prefer to convert into meters per second. So for once, let's do this just to get a feel for this. So 1 mile per hour, what's the conversion? 1 mile is equal to about 1,600 meters. More specifically, I think it is 1609 or 07, I think. I think it is 9, so that's meters. Okay. So you can think of it as 1.6 kilometers. If you're staying in two significant digits, that's 1.6 kilometers. That's a conversion, and 1 hour is 60 meters, right? So this will be equal to 1,609 meters, and 1 hour is 60 minutes, and 1 minute is 60 seconds. Right? So that's how many meters per second. If you were to calculate this, and I did not bring my calculator, give me a second, I'll run and get my calculator. Okay, so we were doing 609 divided by 60. Oh. Sorry. So this comes out to be 0.4. So 0.45 meters per second. Right? It's too significant. Again, let me rewrite this. 1 mile per hour is equal to 0.45 meters per second. Right? That's nothing but 0.5 meters per second. Right? That means to say that for every 2 miles per hour, this is approximately 1 meters per second. This is for insight. You shouldn't be doing this for real problems, but just to get a feel for what meters per second is, whenever you're given some number, a speed in miles per hour, just divide by 2, and that's close to what it is in meters per second. To one significant digit, it'll always be true. So 50 would be 25. Make it one significant digit is either 20 or 30. So it's somewhere between 20 to 30. So let's say 20 meters per second. That's useful because you will be working all your problems in meters per second. And if you really want to connect with what's really happening while you're driving a car, you look at your dashboard and you see, oh, how much is this in meters per second? You want to just divide by 2. So that gives you to one significant digit. So 50 miles per hour, but more exactly, we want to actually talk about how much is 50 miles per hour. So 50 miles per hour is 50 into 0.45, right? So 50 into 0.45, that's 22.5 to 2 significant digits. It's 23 meters per second. Right? So let's say you're driving a car which is moving at 50 miles per hour, which is equal to 23 meters per second. You immediately convert that, and you see a red light. Right? Somewhere here there is a red light. Right? So that's a light, and you see that it turns red, and you want to stop. And let's say you immediately stop. Usually what happens is that there is a small delay in the time you're seeing the light, and from when you press on the brakes, that's called reaction time. It takes a certain amount of time. It's a fraction of a second. It's less than a second. For some people, it's 0.5 seconds. Some people, it is 0.3 seconds. So how attentive you are. If you are in a heated discussion with a co-passenger, that can really be long. Sometimes it can be 1 and 1.5 seconds, and that's what can cause accidents, as you're familiar. But let's pretend that reaction time is 0 in this example. In your homework, you do an example where there is a small reaction time, and then you have to account for that. But in this example here, let's say immediately you press on the brakes. So that's your initial point. Right? So that first recognize what is the initial point, and you press on the brakes, and you reach a final point here. Right? And at that point, it stops. Right? So V final is equal to 0. So two information given to you, and let's also say what is the acceleration. When you press on the brakes, based on what kind of surface it decides how quickly you're going to stop. So let's say that is decided by acceleration, and acceleration is, let us say, 10 meters per second square. So this decimal point means that that's two significant digits. So 10 meters per second square. This is going to slow down the car. Initial velocity is going forward. It has to decelerate if it has to stop. So acceleration has to be in the backward direction. If your acceleration is positive direction, it will speed up. So 10 becomes like 23 becomes 25, and it keeps increasing. If you want to slow it down, you want to accelerate in the backward direction, or you want to decelerate. Well, that's a negative sign, right? In the problem, either you will use the word deceleration, or you have to figure out that since it's slowing down, it has to be negative. Get our equations. There are 5 variables, so we have to recognize all of this 5 variables. So this is V initial, V final. So V initial is 23 meters per second. So positive direction is to the right. This comes to be 0, and acceleration is minus 10 meters per second square. That's 3 variables given to us. And now we can frame a question, and we can ask how far, how much distance will it take to stop? Right? If you're moving at this speed, which is a reasonably high speed, 50 miles per hour, but you can, of course, on an interstate go faster. This is how much time it will take for you to come to a stop, right? So let's ask, so question could be, what is the stopping distance? How much distance will you travel before you come to a stop? Just because you press down the brakes doesn't mean that you will instantly stop. So it will still move forward. And let us say it took, you decelerated at this rate. There are different rates possible. Let's say this was a reasonable rate at which you came to a stop. So you're asking, what is delta x in this scenario? So that's the stopping distance. And notice, even though we are asking for this, there is one variable usually doesn't play a role at all in the discussion, and that's what we will call as a missing variable. Even though it is not asked for, we want to identify so that that will tell you what the equation is. Now look for, once you recognize that delta t is missing, go back to, if I can go back to, yeah. So if you go back to this first part of the board, 5 equations, we want to see which equation has delta t missing. We recognize that time was missing, so it has to be this equation. So we immediately write that down. So going back to that board, so I recognize that, oh, this is the equation that's useful in this scenario. This is just a prescription in this simple scenarios. It works. Very soon we are going to do compound problems, and this does not work very smoothly. Like this idea of being able to figure out which equation we are using doesn't work out immediately, and that's a challenge. That is one of the skills we have to learn as to which equation to use. That will become one of the challenges very quickly. But once, let's say that we know which equation to use, and in this case, we have a prescription, find the missing variable, then it is just put in the numbers, right? V final is 0, that's 0 square, that's 23 square, plus 2 times A, which is minus 10, and delta x, that's all. Right? Put this on the other side, so it is 2 times, it becomes positive when I come to the other side, is equal to 23 square, so delta x is 23 square over 2 times 10. So So that's 23 square divided by 20. And that's about 27, two significant digits. It's 27 meters, right? 27 meters. So notice it still takes 27 meters. A car is about 2 meters in length. So this is about 15 cars, right? That's the amount of distance you still have to travel before you can come to a stop. So that's why it is always recommended that you keep a good amount of distance between you and the car in front of you when you're driving. So that's a simple example where we use this principle. Now let's do an example on free fall. Any questions, comments? Okay, if not, let's do an example. Again, there is a similar problem in the homework where reaction time is not really 0. Okay, free fall. Again, an example. This also is related to the problem in your homework. And at this point, I should also say that most of the problems I will ask in the exam will be very similar to the discussions we have already had. Context will be the same. Like if I'm throwing a ball standing on the roof of a building, the context will be the same, but I'll change what is being asked for. Like I can ask, here we might discuss what's the time taken. In the exam, I might ask what is the distance traveled. So you have to be able to change the problem significantly to be able to address various nooks and corners of the problem. So that's how, that's one of the ways you can prepare for the exam if you want to. So, okay, example, let's say there is a ground. So this is ground. And let's say there is a building. So this is a building. And you're standing on the roof of the building. And you throw a stone up in the air. You can throw the stone downward also, but upward, right? So you throw a stone upward, it will go all the way up and it will come down. And notice that, first of all, let's assume that it is thrown right from the point where the roof or whatever distance of the roof is given to us, that's where it is being thrown for. Your height also plays a picture in there, but let's say that it is right from the point of the roof, right? So that's the point of interest, and that's your initial point. And it reaches here. Now, often the question is the moment you hit the ground, its velocity has come to 0. No, that's not what we are talking about. We are talking about the velocity right before it touches the roof. So all our equations do not work if it touches the ground. For that, we will be developing more equations later in the course. But currently, we are talking about a stone while it is in the air, right? And in fact, we are actually neglecting the air resistance also. So it is while it's in the air, that's what we are talking about. So it's right before it reaches the ground and right after it leaves your hands, right? So that's the 2 points. Let's say this height of the building is 20 meters. So that's 20 meters. Right, it's a 3-story building sort of. A 1-story is about 6 meters or 5 meters maybe. So 3 or 4-story building. So that's 20 meters is your height. Initial point is this. That's your final point. Let us say you throw the stone upward. So that's your initial velocity. So that's your V initial. And let's say that's about 5 meters per second. Okay. And let's ask the question, how much, so the question is, how much time does it take for the stone to reach the ground? And that means right before it reaches the ground, an instant, a small, very small time before it reaches the ground. Let's see if everything is given to us or not. 5 variables, right? If we have to use our equations, 5 variables, the delta x, delta t, v initial, v final, and acceleration a. Delta x we know is this is the height it travels. Notice even though the stone actually goes up and comes down, in our kinematic equations of motion, we only have to talk about final minus initial. It doesn't matter how up it went and came down. Our equations take care of that fact. Right? It is understood that it goes up and comes down, even if it comes. So you might wonder, oh, what's the difference between a ball being thrown down versus going up? How does the equations know about that? And we will do an example right after this where you will actually throw the ball down and see how this changes. Okay. So let's say Vi is positive. First of all, delta x, right? It is V initial. So let's say this is 0 meters and that's 20 meters. And everything is positive upward. 0, 20. I could have started with 0 here, but then this will be minus 20 meters. So what is delta x? Delta x is x final, which is 0, minus of 20 meters. That's minus 20 meters. If I choose everything to be positive upward, that's minus 20 meters. Delta t, that's what we are looking for. That's what is being asked for. That's what I want to find out. That's an unknown quantity. Initial velocity, that's given to be 5 meters per second. It's being thrown upward. That's plus 5.0 meters per second. That's 2 quantity. V final, we don't know with what velocity. It will keep going. It will go slow down, reach on the top, and then come and reach at the bottom. And that's right before it reaches the bottom, but we don't know that velocity. Right? And what is acceleration due to gravity? It's not given in the problem at all. No one mentioned it, but this is free fall. Right before this, we talked about free fall. Anything, if it is freely falling, if you're not holding it, if something is not resisting it, like air resistance, then it has to be falling with minus 9.8 meters per second square. Before I proceed, a couple of extra credit problems. What is its, so when a ball goes up, what is its velocity right when it reaches the top? Suppose I ask you all, what is its velocity when it reaches on the top? Anyone can answer?
Is it 0?
It's 0, right? Trivial, probably trivial. But now let me ask, when it is right on the top, what is its acceleration? Acceleration is change in velocity over time, remember.
0.
Would it still be 9.8?
That's the correct answer. It's 9.8 and it's downward. Notice that's a constant, right? It will keep doing that. But then how do you have it constant when it is right there? One of you I heard said 0, right? Acceleration. So extra credit problem, right? Second one for today is what is the acceleration of an object when it reaches the highest point where its velocity is 0. Right? So its instantaneous velocity right at that point is 0. What is its acceleration? Right? Does velocity equal to 0 mean that acceleration is 0? Right? Apparently not, because I said yes to that answer, right? That acceleration is still minus 9.8 meters per second squared. That's the correct answer. But how come if velocity is 0, how come acceleration is not zero. In fact, it is a constant. Okay, that's the question. Is that clear? Okay. What is the acceleration of, or how come the acceleration of the object is minus 9.8 meters per second square when velocity is zero right on top? Remember that acceleration is change in velocity over change in time. Change in velocity is a difference between two velocities. So that's one extra credit. Right, I have one more extra credit problem for you. So 9.8 meters per second square turns out to be a very special number. That's the rate at which things fall on the surface of Earth. But it's only special if you're on the planet Earth, right? Almost everywhere on the planet Earth, it falls at the same rate because almost all of us are at the same distance from the center of Earth. It is the mass of Earth that decides, and the radius of Earth also matters. So if you're on another planet, this number will not be the same. For example, on Jupiter, this is about 32 meters per second square. That just happens to be, it depends on the mass and radius of it. But since it depends on the radius, you might think that what will happen if you get closer to the Earth. Let's say you dig a hole, very deep hole, and you go down closer to the center of Earth. How does it change? That's one question you can ask. Second is, what if you go up, right, away from Earth? How does it change? Now, generally, it gets weaker. Right? So if this is your planet, and as you get farther and farther, so if this was R, and let's say this is your radius R, the acceleration due to gravity G is related to, if the correct expression is, that is a constant G, like it's called the gravitational constant. I haven't introduced you, that is the mass of the planet divided by R squared. So as the distance increases, as you go farther and farther, this gets smaller and smaller. Right? So if you are, for example, way above on a mountain, for example, mountains are only 10 kilometers. What's the radius of Earth, by the way? It's very large. It's 6,400 kilometers. So R is 6,400 kilometers. And Mount Everest is only about 10 kilometers, very small. But if you're on International Space Station, like International Space Station is significantly farther, not within the scale again, the radius of the height h, right, above which the International Space Station goes, is 400 kilometers. Still very small compared to the radius of Earth, but significantly larger. Right? Now, you have all seen movies or probably YouTube videos about International Space Station. You see things floating around. If you have not, I'll encourage you guys to look into videos on International Space Station. Now, the extra credit question is, what is the acceleration due to gravity in International Space Station? Any guesses before you go ahead and work on it at home? What do you expect will be the acceleration due to gravity in International Space Station? No answers? Okay, so that's the extra credit problem. I was expecting that many of you might say it is zero because things float around. And the answer is no, it is not zero. So, so that's what the extra credit problem is about. So that should be raise some curiosity about what G actually is. So with those two extra credit problems, let's proceed and work on this problem. So we have three quantities known now, right? So this is known, this is known, and that is known. This is the unknown, so that's a missing quantity. So immediately I look into my equations. Which equation does not have V final? And it turns out it is delta x is equal to V initial delta t plus half a delta t squared. plug in the numbers so that I can solve for delta t, and that is minus 20 is equal to 5.0 delta t, and that's plus half of A, which is minus 9.8 times delta t squared. And I'm looking for delta t. So delta t, this turns out to be a quadratic equation. So let me write it onto the left. So this is 9.8 divided by 2, that's 4.9. Bring it to the left, so this becomes 4.9 delta t squared. Bring this to the left, so that's minus 5.0 delta t, and there is minus 20 already, that's equal to 0. A quadratic equation has solutions of the form minus b plus or minus b square minus 4ac divided by 2a. So that's minus b, that makes this minus of minus 5. That's minus b plus or minus square root of minus 5.0 square. That's b square minus 4ac, that's 4 times a is 4.9 and c is minus 20. So remember your quadratic equation, right? So 2 times a divided by 2 times a, that's 2 times 4.9. Right? That's your number and how. Yeah, it's okay. I was suddenly afraid that this is a negative quantity. This is negative times negative, that's positive, so it's added. If by any chance you get a negative number here, this becomes a complex quantity, like square root of a negative number doesn't exist. So that means you made some mistake. This will always, if it's a realistic problem, this will always come out to be possible. So that's 20 times 4.9 times 4. It's 392 plus 25, and it's square root of that. Oops, I made a mistake. Okay, so 4.9 times 4 times 20, 392 plus 25, 417. And it's 20.4. So let me write this as, this is plus 5, plus or minus, this is 20.4. I can make this 20 if I'm working in 2 significant digits, divided by 9.8. And that is 2 answers in there. If I add 5 to that, that's plus 5 divided by 9.8. One of the answer is 2.6 seconds. And the other is, if I were to subtract it, that's also perfectly fine. 20.4 equal to divided by 9.8, right? That's also a mathematically a solution, right? Or minus 1.6 seconds. Right? At this stage, you have to be judicial that you started your time at t equal to 0 here. So whatever happens at this final point has to be in a forward time, which is positive, right? So this has to be the correct answer. So you use your judgment and say that this is positive and that's negative. That's okay. That's the correct answer, and that finishes the problem. And once you have this 2.6 seconds, one could also ask as a second part, or in another context, I could be asking what is the final velocity here. And once you have this time, I can use any one of the equations together, because most of the equations will have time or v final in it. And now that I have 4 quantities, I can use any one of those equations to get v final. That's perfectly fine. But let's explore, does this have any meaning? Right? This minus 1.6 second, what could that meaning be? Of course, it is true that whatever it reaches the ground actually in a forward point, so that's 2.6. But what else is the meaning of that 1.6? So let's look at this diagram again. So this is This is what is happening in here. That's your initial and final. Right? That's your initial point, and that's your final point. And it took 2.6 seconds apparently. But notice our equations do not know that there is a roof or there is a ground. Right? Our equations don't know. That's a physical implicit in the story we introduced that. So our equations don't know that. So then you can ask, oh, how will our equation interpret this final point? That is one more, that this is the complete story is that this is actually coming somewhere from the past all the way from minus infinity and is going to plus infinity. We are just restricting our analysis to this final point and initial point. It comes from down somewhere as far as an abstract equations goes. Our equation says it comes from the bottom and goes to the top, comes to the top, and then goes to the bottom. And you can say this time it takes to, if you were to project this motion backward, that's what this minus 1.6 seconds is. So it is not completely meaningless. That's minus 1.6 seconds in the backward direction. And that you will see this time again coming in. There is a complete symmetry in the problem that you go up or down. So let's explore the question. Let's change this a little bit. So let's see if I can change the color of this. Yeah, so I think this likes pink. Does this look different color? Slightly? Maybe not. No. Okay. So there's no other. Let's see, blue. This. How about this? This is better? Blue? No?
No.
No. Okay. Forget it. Okay, we'll work by making boxed quantities. Okay. So now let's change the problem. So everything, the context of the problem remains exactly the same. I'm going to change very slightly, and that is that the initial velocity, this person threw the ball up in the air. Instead, you throw it down with the same magnitude. So this is now different. Right? It's going down. Right? That's the only change in the problem. Of course, it will take a shorter amount of time, right? It doesn't have to go all the way up and come down, so it's expected to take smaller amount of time. And again, we ask, what is that time? So what is changing is this negative sign. Question? No. Okay. So that's the change, right? So boxed quantity. So there is no box here, except at the end. So this is what I have changed. Right, so this is now negative. So what changes if that initial velocity was negative, right? Rest everything stays the same. You travel from initial to final point, the same distance. Acceleration due to gravity is the same. This is missing. That's what you want to calculate. What will change then? So we go around here. That's the initial. That's going to change, right? This now, instead of being a plus here, this was a plus, I had to put a negative sign there. So that's a change. That's a box. That has changed now. So this equation changes to this. If this changes, when I bring to the left-hand side, positive became a negative. So the top one is negative, but the negative will become a positive, right? So this will change. That's the change. If that changes, what happens here? This now is negative, this becomes a positive. That's a change. And the same thing here. But notice this is squared, so that doesn't change anything. This is an innocent, or we don't have to worry about that. This changes sign, right, to plus. That means this becomes negative, right? So this was actually plus before. Now this will become negative. That's the only, so all over everything goes through except this final answer becomes plus or minus another more than two possibilities. So what happens is that this will become negative in this new scenario, so boxed quantities. So this was plus before, this will become negative, right? That's the boxed quantity. And here, this was a negative, that will become a positive quantity. So you say that, oh, that's 1.7 seconds. The same thing again shows up, but this time it is going in this direction. So the same graph, because of the symmetry, it is equivalent to saying that it was going this way. So this is going, this time is 1.6 seconds, and the other is 2.6 seconds. So that's a very nice observation to make that, oh, that's two different, that's the same, that other time also has a meaning in there. So that's a lot of essence of whatever we are doing here. In the last, I have less than 10 minutes. Let me do one more problem. I'll be very quick and most probably not be able to finish it, so I might hurry a little. But look into the homework solutions. As the same problem is discussed in there also. We want to talk about that. So let's say, so this is often, let's call it example again, right? Example. Oops, I've changed the board probably. Right? So example, I often call it the speeder and cop. This is an example where you compound the problem. So in these cases, this is very linear, 5 variables, 3 equations, three are given and 2 are unknown, right? That is, so there's this nice prescription one can follow and get it. But not all problems are like that. Very quickly, you can compound the problem by saying that there are 2 objects moving, there are 2 independent things going. And remember, time is common for all of us. Like whether it is a cop moving or the speeder moving or any one of us moving, time is common. So that's some observation one has to make. And let's say there is a speeder which is traveling along a straight line. And let us say this is you going with uniform velocity. Uniform velocity, remember, means acceleration is 0. There is only one equation then. That's just simple one equation. So that's delta x for the speeder. So this is xs is equal to, let's say it's velocity v, right? So there's a speeder which is going with a velocity v is equal to, let's say 80 miles per hour. Let's approximate it to 40 meters per second. So it's exactly 40 meters per second. Like remember, it will be slightly more than 80 miles per hour because it is not exactly half, right? And this is velocity v times delta t. Right? That's all. That's the equation for speeder. Since it's moving with uniform velocity, there is only one equation. The cop, let's say, is also moving in the adjacent lane, but the cop is moving with uniform acceleration. And that's necessary because let's say the speeder is moving and the cop, let us say, was at rest. The simple generalization you can make is, what if he was not at rest, he or she was not at rest and had an initial velocity, then how does this problem change? So those are the kind of extensions I make to a problem so that it can be asked in another scenario. And let's say its initial, cop's initial velocity is 0. So the cop starts from 0. But since the cop is accelerating, eventually, however small acceleration it is, eventually he or she will catch up with the speeder because speeder is just going with constant velocity. It has to keep steadily going. However long it takes, eventually the cop will catch up if the cop is accelerating and the speeder is not accelerating. That's not a real scenario. Typically, speeders also have the choice to accelerate. So that complicates it, but we are making it simpler. Right? So since the cop will accelerate eventually at a future point, right, they will again cross. The cop will cross the speeder, and that's your final point. And the question could be, at what time does this happen? Right? Now, the point here is that the time taken, whenever this happens, see, there's a the important fact that time is common for both, and whenever they cross, both the time is the same and the position is the same because they have traveled the same distance. So as far as COP goes, we have delta x is equal to V initial for the COP plus half A delta t squared. Now notice I immediately wrote this equation down. That's not very obvious why I would use that equation. It comes from experience. Why? Because we are actually talking about the distance that the COP has traveled, right? Distance. So that's one of the equations, and initial velocity is 0. So that guides me to calculate, use this equation. So it's an important or a significantly hard step to write that equation down, and that's where many of you will struggle, and you should learn your ways to figure out which equation to use. And let's call this the COP, right? Delta xc is equal to half A delta t squared because this is 0. And I have a minute or so. Now the important point here is that the same distance, they travel the same distance when the COP is catching up with the speeder. It's exactly the same distance both have traveled, and it is the same time that has evolved. So I can put in both in here. So that's half A delta t squared. And I said velocity is 4 meters per second. I should also say for the acceleration of the COP, let's say it is 3 meters per second squared. So that's an information I should give to describe the COP's acceleration. So one of the time cancels out. So the time it takes for the COP will be V times 2 divided by A, which is 2 times velocity I said was 40 meters per second divided by 3, which is 80 divided by 3. So that's about 23 seconds. Right. So this is 23 seconds. That's the time it evolves. Once I know the time, I can actually calculate the distance, either use this equation or that equation. So notice there are a couple of things that happen here. This is coupling two motions, uniform velocity and uniform acceleration. And I'm using the fact that the positions are the same or the time is the same. And there are other problems in your homework where there are two distinct things happening and you have to compare the two. You have to couple the two problems. Usually time is the coupling factor in between them. And again, look into the solutions also. That should help. It's almost, I've written it in a descriptive way and changed the numbers and all. So I'll encourage you to look into that. But before you attempt on that, do attempt on your own before you look into the solutions. If you're looking into the solutions, assess yourself or be responsible about putting in more time. Work on example problems in the textbook also. And thank you. I did 2 minutes extra. Sorry about that. Any
You turn in
comments?
just one extra credit question, or do we do all 3 of them?
All 3. Just list all 3. Again, don't spend more than 5 minutes. I don't recommend you to spend more than 5 minutes if you're working for the grade. If you're doing it for exploration, please go ahead and spend as much time as you want. This is just to raise curiosity about the concepts that's being discussed. Helps?
I have a question.
Yes, please.
Can you please go back to the original problem where the stone was being thrown off the building?
Oh, yeah, sure.
I am confused as to, so like in the first example that we did, we're trying to set the equation to 0 to make it a quadratic. Why didn't you just add over the -20 to make it 0? Like, I don't understand why 20 is negative there.
Because it was negative to begin with, right? Because it is going down.
Well, right, but to set the equation equal to 0, wouldn't you add it over to the other side?
Oh, so there are 2 ways. If you add it to the other side, this will be negative.
Right. Oh, I see. So you want
all of those things to left side. I didn't take this to the right side. I brought these two to the left side.
Okay. That answers my question.
Great.
Thank you.
Good question. Yeah. Feel free to ask this right when I'm talking. Don't feel that would have helped everyone, but that's okay. I understand that it might be harder to ask questions. Good.